Yes, today we're going to see in the third lecture the second part of the control theory. Control theory, what we see, you have optimal control minimization problem, but controllability is another, topic that is part of control theory, but is a little bit different from minimizing functional. They are related, but it's really not directly minimizing functional. Then we will talk about interior control and exterior control. Interior control, we will see that our control is inside the domain where we have our PDE, and exterior is that our control will be outside where we have our PDE. Then, like we say, we will discuss the controllability of fractional PDE. Then we consider the two types of control, the interior control and the exterior control. But like I mentioned that in lecture 1, that those problems may be difficult, very, very difficult to solve. But in our lecture, in each of the results, I will try to give a characterization of each result we want to prove. But it does not mean that the characterization is easy to prove. We have a characterization, but the characterization may be very difficult to prove. But there are still, nowadays, really a very beautiful math that is being developed for people working in control theory to try to, to solve some of these problems. And then, really, most of the topic we will discuss today, each one has an open problem that we cannot solve for the fractional Laplace operator. Then let's start the first one, the interior control. Then here, omega is a boundary domain, and we consider that is the control problem. Then minus delta S that we know now is clear, the fractional Laplace operator. Y is the state, that's what we want to control. And F is our control function. And the control function is localized in an open subset of omega. Then in some sense, we tell you control theory, we will see up to a controllability is that, okay, I have here my domain, I have here my dynamical system here. That's here. Then I want to see, okay, if I have an information only on small omega, if I can recover all the information on all, for all my dynamical system. That is controllability. I will make a partial measurement on omega, on small omega, and I want to recover all the information. That is the main goal of controllability. Then first we have to define here what we mean by a finite energy solution of our heat equation is only a function u that is in L2 with value in HS0, and it's in H1 with value in the dual that coincide, at 0 is the initial value, and we have this equality that we defined also yesterday like a solution for our heat equation when we have 0 exterior condition. Of course, the epsilon of UV is exactly the energy form that we have seen yesterday. But to tell you that the Lyon's results say that the spaces where we have the finite energy solution is embedding continuously in the space of continuous function on 0t, such that saying that y of 0 is y0 really makes sense because we have that our solution is a continuous function. Then one can prove that for any y0 in L2 and F with value in the dual, you always have a unique finite energy solution. And also, if the initial condition is 0, or you don't need even 0, and F is in L2, the finite energy solution is nice. It's only in L infinity and also H1 in L2, such that we even have a strong solution for our problem. But in any case, the solution is given by the variational constant parameter is given by here is the semigroup. the semigroup applied to the initial value, and here is the convolution between the semigroup and your non-homogeneous term f. Okay, always the solution is given by that, like what we have seen yesterday, for when we have 0 exterior condition exactly for the Laplacian if you have 0 boundary condition. Then if you have that, what are the set that we can reach? What we call the set of reachable state is the set of y, the set of all y at value of capital T and f run in L2 of 0t times omega. Where we take our control function f, then it is set the whole solution at t when f is in the set of controls. Then from that, one can define, you have three notions of controllability. The first one is what we call null controllability. Then we say that our system is null controllable in time t if and only if 0 belongs to the set of reachable state. And this is equivalent that you can always find a control function f such that your solution is identically 0 at time t. It's exactly equivalent. The second one, we say that the system is exactly controllable in time t if and only if the set of reachable state coincides exactly with L2 of omega. If we can reach all L2. Then that is equivalent that if you have a target, yd, you can find a control function such that your state coincides exactly with your target. And the last one, that's what we call approximately controllable. That is equivalent that the set of reachable states is dense in L2. Then this means that you give any initial condition in any other vector in L2 and epsilon positive, you can find a control function such that your solution is close to y1 in the sense that the norm is less than epsilon. Then those are the three notions of controllability we have. Then we have null controllability, exact controllability, and approximate controllability. But the most important property of the heat equation is his regularizing effect. The heat equation is really regularizing. What does it mean? When omega, the small omega is not exactly all the set, then solution of the heat equation are C infinity at time t in omega. Then this means that the restriction of element of the reachable state are also C infinity function on capital omega minus small omega. Then in this case, then if you take omega, where you want to control to be the whole space, then you cannot have null controllability. Doesn't make sense. Okay? Then it's always you have to take that your control region must be a smaller one. But this is due to the fact that the strong time irreversibility of solution of the heat equation. Because heat equation solutions are not is irreversible in time. Now, let's see the first one. One can prove that, okay, the system is null controllable if and only if it is exactly controllable. For the heat equation, null controllability is equivalent to exact controllability. How you see it, okay, it's clear that exact controllability implies null controllability because exact controllability means that you give a target to yd that your solution at time t coincides with the target. Then I will take my target to be 0. Okay, then exact controllability implies null controllability. Now, if we assume that the system is null controllable, then any initial data may be lead to any final state to the form S of t y0 with y0 in L2. That is in the range of the semigroup. Why that? Because if you give me y0 and z0 in L2, you take that like initial value, the set of reestablished set of y0 minus z0t is the set of reestablished set of y0 minus the semigroup at time t applied to z0. But since 0 is here, because we assume that it's null controllable, then necessarily S of t z0 must be here. Then we have proved that null and exact controllability are the same for the heat equation. Now how we prove a characterization of null. Here null and exact controllability is the same. One can prove that the system is null controllable in time t if and only if you give me any initial datum y0. Here it is in omega, everything is omega, it's not minus 0, 1. Then you have a control function f such that here the integral of omega y0 v0 is equal to this integral of the control function. Here v is the solution, what we called yesterday the adjoint equation or the backward equation. It's the equation is, it's the backward heat equation in time. Then here is the final datum. Then this is equivalent to null controllability. Then if you can prove that, you can say that your system is null controllable. How to see it? Let's give the idea of the proof. Then you take V, the solution of the dual problem, and as a test function in the definition of weak solution. Okay, when we define the finite energy solution, we take V as a test function there, and we make the integration by part. Here is the duality map between H minus S and HS0. You integrate in time and in space. You will get y of xt, v of xt minus y of x0, v of x0 plus this one is equal to 0. Then if we know that 1, 3 hold, this means 1, 3, that is the condition that we give here, if that one hold, then this equality will give us that this integral is 0 for every vt in L2. Because this guy minus this guy is 0. Then we just got that this guy is equal to 0. And the fundamental lemma of calculus variation say that y of t is 0. Then we have null controllability. Now conversely, if it's null controllable, if this guy is 0, then you put that in the left-hand side, then you will get exactly 1, 3. Then null controllability is equivalent to this equality. But it's not useful, it's difficult to prove. You cannot prove this equality. Another important thing that one see, null controllability in time t is equivalent to what we call the observability inequality. Which means that there is a constant c such that if V is the solution of the adjoint, the backward system, that the L2 norm square of V at 0 is less than this integral, which means on the control region of the V squared. That's what we call the observability inequality, which means if that one is true, from here, I have all information on all my system. That is very difficult to prove. Even in the classical case, S is equal to 1. The only possibility in S equal to 1, or one of the only, is what they call the so-called Kaliman estimate. I will not go far from the Kaliman estimate, but I'll tell you what is Kaliman estimate. I will write it for the classical case because we don't know it for the fractional equation. The classical case that, okay, if I'm writing using ut minus delta u is f omega, the characteristic function of omega, I have this heat equation. Kaliman estimate say that, okay, if I can find a weight phi of xt and prove that I have here integral on omega, the gradient of u here xt square plus u of xt square. Here I have a s, and phi, no, exponential of 2 times s, phi of xt dx, integration under the cylinder q. If I can find that is less than a constant, this constant does not depend on s, does not depend on u, and integral here, the cylinder of f of xt square and exponential of 2 times s phi of xt dx dt for all s greater or equal to a certain s sub 0. Then if you can find a right weight that satisfies this inequality, you will be able to prove the observability inequality. But that is done by Kaliman in the 1940. Even if you find the right way to find this inequality, you will have maybe, for the classical, you will have maybe 24 pieces that you have to see which pieces you have to put together in order to get this inequality. But for the fractional Laplacian, there is no such a result. No, then we don't know how to prove the observability inequality. Then what we're saying that you see that the observability inequality say that this quantity, if I know this quantity, which means the observed one, which depend only on the restriction of V on the control region, then that one uniquely determines the solution of the adjoint equation. Like I say, it's really difficult to prove even if in the case S is equal to 1. But for the fractional Laplacian, we don't know how to prove Kaliman estimate. It may happen that the exponential is not good here, because exponential here is good because you can compute the Laplacian of exponentials. Then let's see about that. Let's see the comments about, recall that the null controllability is equivalent to that. Then if we can prove that, if that one is true, we can obtain the control with minimal L2 norm about all the admissibles one. If I know that is true. And to do that, we just have to minimize this functional. I define V of J of V0, I minimize this functional on this Hilbert space. This Hilbert space, the set of all V0 such that solution V of our adjoint equation satisfies this condition. But remark that V, the space H is larger than L2. It's exactly the completion of L2 with respect to this norm. And it's a larger space than L2. Then we can prove that G is convex and continue on H. Also, 1.7 say that G is coexistive. Then we can have the existence of minimizer. Then if you prove the observability inequality, you can find what is the best possible control.
So here, the completion of L2 omega, there is no time?
Here?
And the L2, you say L2 omega only?
No, L2 of Q, sorry. Yeah. Then, as we say, we do not know how to prove 1.7. Then if you do not know how to prove it, then you cannot also know how to, even you have a best possible control. But let's see, we have good news in one dimension. We know how to prove it without using the observability inequality. That is a result that is improved by Umberto Bicari and Hernandez. They prove that the system is null controllable for every time t if and only if S is between 1/2 and 1. What is the idea there? You take the eigenvalues of the fractional Laplace operator with the normalized eigenfunction. Then if you put Vk is phi k exponential of mu k t minus t, that is a solution of the backward system with the final value is phi sub k. Then you multiply your initial equation with Vk and you integrate on the cylinder. Then we get that u of xt is 0 if and only if you have this equality. Then if we assume that there exists what we call a bi-orthogonal sequences. A bi-orthogonal sequences that is bi-orthogonal to exponential of mu kt. This means that the integral of q and t exponential from mu kt is the Kronos-square delta of nk. Then if you have a bi-orthogonal, we assume that we have a bi-orthogonal sequences. If we have that, then we can prove that this function will be a control. Then the function given by this series will be a control. And how we do that, there is a theorem by Muntz saying that this is a control if and only if the sequence is, this means the series 1 over lambda k is finite. And there is a result by Fattorini and Russell to say that, okay, if you have this gap condition, which means if you have a constant gamma that is positive, such that the difference between two eigenvalues is greater or equal to gamma for any k, then the L2 norm of your bi-orthogonal sequence is bounded by c times exponential of tau mu k. Then that is those two results that you have to know. Then you have to use the Muntz condition and the Fattorini-Russell condition for the bi-orthogonal sequences. Then the good news that we know the eigenvalues of the fractional Laplacian in the interval are given by this formula plus a big O of 1 over k. It's not an exact formula, but we have this formula. It's given by that. Then you can see that the first one, this condition, the condition on the eigenvalues, are satisfied if and only if S is between 1/2 and 1. Because if S is between 0 and 1/2, you see here the two S is between 0 and 1, that behaves like an harmonic series. Then that one will diverge. Okay? And to obtain the other condition, we have to prove that one can have a lower bound of the L2 norm, L2 of omega on the observation domain of the eigenfunction is bounded below by a constant C that is independent of K. Then if you know that, then you have the Muntz condition and the Fattorini-Russell condition, then you can conclude that your system is null controllable. That's the only condition that you can use. Then you do not know how to prove the observability inequality, you use those two conditions. But in dimension n, it's almost impossible because even unless you have a very special geometry, you cannot have the eigenvalue correctly like in 1D. But what happened in n dimension? In n dimension, what we know recently we had to prove, we know partially how to prove that we have null controllability, but we also don't know, we did not use the observability inequality, but unfortunately, our observation domain has to be what we have here, which means a certain neighborhood of the boundary. It doesn't work for any open set in omega. But if you have that, we can also prove that we have null or exact controllability if and only if S is between 1/2 and 1. Well, to prove that, we change the idea, we go to the wave equation. We use the wave equation, the so-called Lebor-Roviano strategy and transmutation techniques. Transmutation say that I can transform solution of the wave equation into solution of a heat equation. That's what we call transmutation. Then you use the wave equation, and then you try from the wave to come back to the heat. Okay, now it is clear we finish null and exact. What about approximate controllability? It is clear that null or exact controllability always apply approximate controllability, okay? Because approximate controllability, you have that the L2 norm of the difference is less than epsilon. How you see that? Because if you have here the semigroup applied to L2 is always a subset of the reachable state for any Y0 in L2. and taking into account that all eigenfunctions of the fractional Laplacian with zero directly exterior condition belong to the image of the semigroup at time t, then we can deduce that the set of reasonable states is dense, and then we have approximate controllability. Then always null or exact controllability imply approximate controllability, but clearly approximate controllability does not always imply null or exact controllability. Okay? Because we say that if you call this guy the image of the semigroup at L2 at time t, that is dense in L2. Then since it's included here, then you can always say that the set of reasonable states is dense. Now, for the approximate controllability, it is also enough to consider the initial datum to be 0. Why? Because if you take the reachable state with y0 is exactly the reachable state at 0 plus the semigroup at y0. Now, we know that the second one belongs to L2. Then we can deduce that that one is dense if and only if the one at 0 is dense. Then if you want to study approximate controllability, you can just consider that your initial condition is 0 in order to not to bother you in your computation. Now, approximate controllability, you see, together with uniform estimate of the approximate control function may lead to null or exact controllability. If you know that you have approximate controllability, but your approximate control function, if you have a uniform estimate, you can get null or exact controllability, but that will be clearly difficult to get. But how you do that? If you have y1, you have a target y1 that is in your set of reasonable state that is there, if and only if you have a sequences of control that satisfy the approximate controllability, and that is bounded in L2 of 0t times omega. How is that? Because in this case, any weak limit here of the sequences f epsilon of control will give an exact control which make that y of t is equal is exactly y1. And if you have that one is uniformly bounded, then you will always have the weak limit will give you a control function. But most likely to have that is bounded here is not given for the problem we have. Okay, characterization, how we characterize approximate controllability. Then the system is approximately controllable. Everything is done with the dual system. Then if and only if the dual system has the unique continuation property. What is the unique continuation property? The unique continuation property says that if I take my solution here of the dual system, and if V, my solution is 0 on the small set omega, then V must be 0 everywhere. That is the unique continuation property. Then if you have a solution of your backward system, and it's 0 on the small cylinder, then it must be 0 on the big cylinder. Then that is equivalent to approximate controllability. The idea of the proof, then that really, to prove this result is sometimes required to, a fine analysis and analytic continuation property of solution of the adjoint equation by using, analytic functions. And you can also use, the solution that the eigenvalue problem has the unique continuation property. This means that you take the eigenvalue problem here for the fractional directly Laplacian here, then we can say if phi is 0 in small omega, then phi must be 0 on all omega. Then if you can prove that, You need this condition and some analytic extension property in order to prove that you have the unique continuation property. But that is really the key to prove approximate controllability. You cannot prove approximate controllability without using a unique continuation property. Now, in 2019, that we have, at least we have a good news that in any dimension, for the fractional heat equation in any dimension, the heat equation is approximately controllable in any time t and any control in L2. You always have approximate controllability. To give an idea of the proof, if we say from the Harn-Banach theorem to prove that the set of reasonable state R of 0t is dense in L2, that is true if and only if you give me Vt in L2 such that the scalar product, the L2 scalar product is 0 for any y, then Vt is 0. Okay? Now, we take V to be a solution of the dual system with final datum Vt. We multiply the first equation with V, multiply the dual equation with the solution of the forward problem, and you integrate by part. Then you will get this formula that is Fv, that is Yt plus minus delta Syv. Then you integrate by part here on the, you will get here, you put everything on the dual system, the dual solution V, Y, and it will remain this term here. And that will come here, you have V times, that will come from the integration by parts from the fractional Laplacian, V times the non-local normal derivative of Y minus Y times the non-local normal derivative of V. But remember that V is 0 on sigma, Y is also 0 on sigma, then this guy cancel, and this also is 0, that's cancel, and it will only give you Y of t Vt. Then you have this integral is Y of t Vt. Then we can prove that now we can say that, okay, the integral of Yt Vt is 0 if and only if the integral of 0t from the small cylinder of Fv is also 0. But if this integral is 0 for any f, then V is 0 and 0t times omega on the small cylinder. And the unique continuation property say that V is 0 on the big cylinder. And now, since the solution of the dual system is unique, then if the final datum is 0, then the unique solution must be, if the solution is 0, then the final datum must be 0. Because that one tells that the solution of the dual system is 0, then necessarily the final datum is 0. And then you can prove you have that your system is approximately controllable in any time t and any control function. Let's see, we have a variational approach to approximate controllability. What is that? Is to give another proof of the approximate controllability, but the proof has the advantage of being constructive. It's only that we don't prove that it's approximately controllable. It allows us to compute the approximate controls. How we do it, we fix a time t, and we know that we can take our initial condition to be 0. And we let y1 to be a final target and epsilon to be positive. Then we recall that we are looking for a control function f such that the solution y of our heat equation satisfy this inequality. This means yt minus y1 is less than epsilon. Now let us define the functional g epsilon from L2 of omega to r by g epsilon of Vt is 1/2, that is the L2 norm of V square. That is not a misprint, it's not the L2 norm square. It's epsilon, the L2 norm of Vt. It's not square. And the minus integral of omega y1 Vt. Then V is already the solution of our dual system with final datum Vt. Then we define this functional. I claim that the minimum of G epsilon give a control to our problem. Well, if Vt hat is a minimum point of G epsilon L2, and V hat is the solution of the adjoint equation with final datum Vt hat, then F, the restriction of Vt hat to the small open set omega, will be our control, because it will satisfy the condition that we have. That's what we want to prove. Then first, assume that G epsilon attain a minimum point at Vt hat. Then for any V0 in L2 and H in R, then we have that G epsilon Vt hat is less or equal, because it's a minimum. It's less than G epsilon Vt hat plus H V0. Then we can compute that what is this guy, then it's 1/2 the L2 norm square plus epsilon, that is the L2 norm minus that. That is only the definition of the functional. Then we try to just separate them. We get this term H square of V square plus this term plus epsilon Vt plus H V0 minus this one. That one is only, we are computing those terms separately. Then you compute, then you will get that 0 is less than epsilon, the norm of V hat plus H V0 minus the norm of V hat plus the H square and this norm square plus H times this norm minus this one. But remember that this guy, the L2 norm of V hat plus H V0 minus the L2 norm of V hat, that is less or equal to the absolute value of H times the L2 norm of V0. Then since we know that, we obtain that for any H at V0, we have this inequality. That 0 is less or equal to what we have in the right-hand side. From then, we can divide by H. Then we divide by H. We divide that one by H. First by H positive, and we pass to the limit. Then you divide, let's go, you divide by H, but this one there is no H, that one there will be a H, there is no H, there is no H. Then you pass to the limit, then you get that 0 is less than this, what we have here, the L2 norm of V0 plus this integral minus Y0. Then we do the same for H negative, then we will get, in fact, the absolute value of this guy is less than epsilon norm of V0 than L2. Then if we take now F to V, the restriction of V hat to omega, and we multiply 1 by V, solution of the adjoint equation, and we integrate by part, we will get exactly this formula that we already know before, that we get by taking F to be this one. And from there, we can just conclude from the inequality that we prove that it's only y of t minus y1 v0, that this absolute value is less than that, and that is equivalent, that the L2 norm of y of t minus y1 is less than epsilon. And that is exactly approximate controllability. Any questions so far? Okay, but let's see. We just have assumed that we have a minimum, but now we have to prove that our functional has a minimizer. Okay? Then I claim that there exists a minimizer. Well, the functional we define is clear that it's convex and continuous. Then to prove that we have a minimizer, we have to prove that it is coexistent. And coexivity, then this means that this norm goes to infinity. That one, the functional goes to infinity when the norm of Vt goes to infinity. That's what we want to prove. But what we will prove that the lim nth when Vt goes to infinity of the functional divided by the L2 norm is always greater or equal to epsilon. If we can prove that, then of course that implies that we have coexivity. That's what we will prove. First, we take a sequences in L2 of initial datum that goes to infinity, the L2 norm. But we normalize them so that the L2 norm is 1. Now we take V sub j tilde to be the solution with those final data, of the adjoint equation with those final data. Then if we have the functional divided by the L2 norm, then we can compute is 1/2 times the L2 norm times this integral plus epsilon minus this integral. That is y1 times the solution of the dual problem. And that is only a simple computation because we have the formula, we divide with the L2 norm, and we will get exactly this equality. Then if you have this equality, there are two cases occur. What is the first one? That this lim f is positive, what we have here, this guy. If this lim f is positive, then of course in this case that goes to infinity, and we are done. Now, if the lim f is 0, then this means that the sequences v tilde tj is a bounded sequence in L2. Then by taking the subsequences, we can suppose that it converges weakly to a function v sub 0 in L2. And then the associated solution of the backward system also converges weakly to a function v in L2 of in the space where we have the finite energy solution. Then V will be the solution of the backward system with final datum V0 at t is equal to t. Now by the law of semi-continuity, we have that the L2 norm, on the small cylinder of V square is less or equal of the lim f. That is the law of semi-continuity. Now taking V is 0, therefore we can assume that V is 0 here because the lim f of that is 0. See. Then V is 0 on the small cylinder. And you see, we go back again to the unique continuation property. The unique continuation property says that V is 0 on the big cylinder. Then if V is 0 there, and the solution of the backward system is unique, then the final datum V0 is 0. Then if it's 0, then what we have then we can conclude that in factor of subsequences converge weakly to 0 because we have that is converged to V sub 0 and V sub 0 is 0. Then it's converged weakly to 0, then this means we have, and if it's converged weakly to 0, then this guy goes to 0. Then hence we can have that now we can sum all that up. We have this lim f is greater than the lim f of epsilon minus this guy, but this guy is 0 is equal to epsilon. Then we have proved that the lim f is greater than epsilon. Then our functional is coexistive. Then we have a minimizer. Then that is the variational approach to approximate controllability. Here is very nice because you can always construct what is your control function. Then, like say, the second approach does not only guarantee the existence of a control, but also, provide a method to obtain the control by minimizing a convex, continuous, and coexistive functional on L2. But in the proof, this term is the most important one. The term what we put epsilon norm of Vt in L2. Because the coexivity depends heavily on this term. It's not only for technical reasons. Even in the case, if you take epsilon is 0, you cannot have the coexivity even in the classical case S is 1. It's impossible. Okay? And like I said, we always use the unique continuation property. You cannot do approximate controllability without the unique continuation property. Now, let's briefly take the last few minutes and to talk about exterior control, how we still see exterior control. Then we have here our control problem, like the same that we did before, but now our control is outside the domain where we, is outside omega. Here, what I say, capital O is a subset of the complement. Then here is U is our control, is the state that we want to control, and G is our control function. We also here in lecture 2, we know what we mean by a very weak solution, because here G is in L2. By a very weak solution, we mean that that's what we wrote yesterday, that the integral of U times the backward system is equal to minus G NS of V. Then remember that V is the solution of the backward, the dual system. Then that this very weak solution that we will suppose here. But also here, the set of reasonable state is given by U of t, G is in L2. But notice that, using theory of evolution equation, we do not have a problem at t. At 0, we do not have continuity of solution at 0, but at t, solutions are well defined at t, far from 0. Then that's why this set makes sense for G in L2 of 0t times omega. But we cannot take U of 0, you cannot, because U is not continuous at 0, it's not well defined. Then also here, as in the case of interior control, null controllability is also exactly equivalent to exact controllability. Okay, the system is null controllable in time t, if and only if the system is exactly controllable. The proof is exactly the same. Also, now let's characterize the first characterization of null controllability, that the system is null controllable if and only if that we have, like before, the integral of u0 w of x0 is now the integral of 0t times integral on our control region of g times the normal derivative. Before, we don't have the non-local normal derivative. If you take an exterior control in your characterization, it's called the non-local normal derivative of the solution of the adjoint equation. Okay, then Wt, the final datum that is in L2, and remember that the non-local normal derivative is defined by that, which means it's leave outside omega. Then also here, we have the observability inequality, that the system is null controllable if and only if we have this observability inequality. Which means that the information on the normal derivative of the solution of the backward system will determine all the solution of the backward system. If you know, if you have an information on the non-local normal derivative of omega on your control region, you have the information on what happened in all your system. That's what I said before. Nobody knows how to prove this observability inequality. You don't know. Even the first one for the interior control that we don't have, that we just have only here f, we just have integral on, inside omega, not outside. Nobody knows how to prove. Here also, we do not know how to prove that this observability inequality. But in dimension 1, here also we have proved it in dimension 1 first by using exactly the same ideas, because remember that controllability is really based what the behaviors of solution of the dual system. Okay? Then also here we all use the bi-orthogonal sequences. We also the gap condition, the Munn's theorem, and the Fattorini and Russell theorem. Then for the interior control, we don't know. For the exterior control, we do not have any result like we have for the interior when omega is a certain neighborhood of the boundaries. Don't. But here the difference here, the proof here, the first difference, okay, but orthogonal sequence is done by the same. The gap condition is the same. But the Munn's condition, remember here, we have the normal derivative. Then we have to prove that we can bound the L2 norm of the non-local normal derivative of the eigenfunction on our control region. We can bound it with a constant that does not depend on L. We can have to find a lower bound on our control region. This means that here, like when you write it, we need to bound that the L2 norm of phi n, not phi n, ns of phi n than L2 of our control region is greater than a constant. That is the difference with the integral control. If not, the gap condition is the same eigenvalues, because the adjoint equation is the same eigenvalues, then you have the gap condition. Then you can, the bi-orthogonal sequences, you will have it under this condition, but you have to prove this condition. Remember that O is a subset of the complement of omega. Then here also we can prove approximate controllability. Okay, the approximate controllability is also the same. You can take U0 is 0, but also here we have proved in any dimension that the system is always approximate controllable if and only if the dual system has the unique continuation property. But here, what is the unique continuation property? That you take V to be the solution of the dual system if the non-local normal derivative is 0 on any open subset outside omega, then the solution must be 0 on the cylinder. Then you see, as it means that the non-local normal derivative is 0 outside. Then that must imply that my solution is 0 on the cylinder where I'm solving the equation. That is the unique continuation property for the non-homogeneous exterior condition. And if we can prove that, that is equivalent to approximate controllability. But we have proved in 2019 that the system is always approximately controllable in any dimension and any control function. Then the proof, like before, you just have to make the right integration by part. Then you take the solution of your equation and V the solution of the adjoint equation that is really smooth. And using the definition of very weak solution, you get exactly this guy. Then we have here that 0 is equal to that, because that one is 0. And from there, to prove that this set exactly is 0, you just have to use exactly the Hahn-Banach theorem that if this integral is 0 for any g, then for any g, then Vt must be 0. Okay? But from what we have here, that one is 0, and before, and this difference is 0, then give you that the integral of g times ns of v is 0 for any g here. Then the fundamental lemma of calculus of variation say that the normal derivative is 0 on 0t times O, and the unique continuation property give you the solution of the backward system is 0. And if the solution of the backward system is 0, then since the system is linear, then the final datum is exactly equal to 0. Then we have approximate controllability. And that's what we concluded. Then I just give some few references where you can find more information on those kind of topics. Then, yeah, thank you very much, and happy to take any questions. Yeah.